Okay, we're pushing into chapter 20, which is on carbonyl chemistry and oxidation and reduction. So we're skipping chapter 19 for right now. We'll come back to it later. But we'll go through all of chapter 20, not right now. This will just be an introduction to it. And we're going to focus on oxidation and reduction reactions of carbonyl groups. This will include aldehydes and ketones, but also carboxylic acids, esters, acid chlorides, and amides. If we want to recall what we learned from chapter 12 with alcohol oxidation, how you can synthesize carboxylic acid and aldehyde groups or ketones, so how we can make carbonyls, is through familiar reagents, chromic acid and PCC. If you have a primary alcohol, you have two different possibilities. If that primary alcohol is effectively oxidized twice with a strong oxidizing agent like chromic acid, you get the carboxylic acid. PCC is a milder reagent that stops at the aldehyde. And so these are reactions you should know. If you have a secondary alcohol, well, it can only be oxidized once anyway, so chromic acid or PCC give you the same product. So that's old news. Turns out you can oxidize aldehydes as well. So if you have an aldehyde, that can easily be oxidized up to the carboxylic acid simply by using chromic acid, or potassium permanganate also works. So these are almost interchangeable in their use. They're both very strong oxidizing agents. And so, for example, we can take an aldehyde and oxidize it to the carboxylic acid. And just another example of an aldehyde using the other reagent. And these are all very straightforward reactions, no rearrangements or anything like that. You don't need to worry about the mechanism. It's kind of complicated involving the metal. But we can get acids as products here as well. And so this is new. Now with these carbonyl groups, we can also reduce them. Basically have two different choices for reducing reagents, and these are extremely common reducing agents throughout organic chemistry. We've already been introduced to lithium aluminum, well, we've been introduced to both of these, but we've been introduced primarily to lithium aluminum hydride, a very strong, common reducing agent for many different functional groups. Sodium borohydride is commonly reacted in methanol, or other alcohols, or even water is possible. Lithium aluminum hydride would be reacted by itself, followed by a water step. And that's important to remember. These reagents effectively act as a source of H-. But because the metal's there, it doesn't just act like hydride, like sodium hydride, won't necessarily reduce these kinds of functional groups because sodium hydride is much more strongly basic. These allow the hydrogen to act like a nucleophile instead of a base and form bonds to carbon. And we can see how that will bear itself out. So for example, we can reduce aldehydes with either set of conditions. And these get reduced down to alcohols. And effectively the mechanism, and this isn't truly doing the mechanism justice, so I'll put it in quotation marks, but effectively it's as if H- is attacking the carbonyl carbon as a nucleophile. And so the carbonyl carbon, as we've been introduced to before, is very much partially positive. The oxygen is partially negative, and so it attracts nucleophiles to it. And so H- can go in and form a bond that breaks the pi bond of the carbonyl. And so it's useful to think of these reagents as acting as a source of H-. The alkoxide can then get protonated from our alcohol in these situations. To get to the neutral product. We can also reduce ketones in a similar fashion. Aldehydes will get reduced to primary alcohols, since they're at the end of the chain. Ketones will become secondary alcohols. And the mechanism is essentially the same. We're treating lithium aluminum hydride as simply a source of H-. H- attacks, you get an alkoxide, and in this case it would be protonated by water instead of methanol in the workup step. But ketones make secondary alcohols. Hydrogenation can also work to affect reduction of ketones or aldehydes. In general, it works well. Usually lithium aluminum hydride works better. But for example, a simple ketone can be reduced effectively under these conditions as well. The mechanism's totally different. We don't need to know the hydrogenation mechanism, but it's another option for reduction. Where this can be handy is if you want to have selectivity and reduction of different functional groups. Specifically, when alkenes are involved. If we have a molecule that has both a carbonyl and an alkene group on it, we can selectively reduce different groups. For example, with lithium aluminum hydride or sodium borohydride, they're only going to reduce polar pi bonds. And so they can only reduce the carbonyl group. And so they'll leave the alkene alone. With hydrogenation, although it's hard to administer selectively one equivalent of hydrogen, it can be done. More easily reduced or hydrogenated pi bond is actually the alkene. These are reduced extremely easily. And so the first equivalent will pretty much always reduce the alkene. And so if you're able to administer just one molecular equivalent, you can preserve the aldehyde group. Now, if you wanted to reduce both of these in one reaction, you have the power to do that just by using excess hydrogen. To get down to just the alcohol. And so there's all sorts of possibilities depending on your choice of reagents, and in this case, the stoichiometry of the hydrogen. Now it would be useful to go back and look at your carboxylic acid functional groups and their derivatives. They're all related, they're interchangeable through reaction, as we'll see in subsequent chapters. But in terms of their reduction chemistry, they're very similar. And so the functional groups of interest are the carboxylic acid, a group known as an acid chloride that we've seen in Friedel-Crafts chemistry for the acylation, the ester, and the amide, or amide. For reduction of all of these groups, the most common way to do it is with lithium aluminum hydride. So this reagent, if you only remember one reduction reagent, it should probably be lithium aluminum hydride. It is extremely versatile and powerful. However, milder reagents exist. For different functional groups. That do not reduce completely. So for example, they'll stop at an aldehyde instead of reducing all the way down to an alcohol. And I won't go over them now, but they can be found on a page in your textbook. Lithium aluminum hydride will reduce a carboxylic acid all the way down to the primary alcohol. So it's kind of two reduction steps. Of course, we can go the other direction with chromic acid. And so you can go back and forth and you can think of how these reactions are extremely useful to know for multi-step synthesis problems. As an example, any carboxylic acid will do. They can all be reduced. The number of carbons doesn't change. Essentially, we're just removing that ketone. Now, this is different than like the aryl ketone reductions we saw, the Clemmensen reduction or the Wolff-Kishner reduction, where the carbonyl was taken out. Those conditions do not work with carboxylic acid derivatives. They're different functional groups. So lithium aluminum hydride strictly works with these functional groups. If you think about the mechanism, again, we're cheating a little bit and oversimplifying the mechanism. But if you think about these reducing agents as sources of H-, basically it's as if hydride is acting as a nucleophile and attacking the carbonyl carbon. What can happen from here, because this is already really basic solution, we first attack at the carbonyl carbon, make an sp3 tetrahedral intermediate. When these electrons come back down, they can kick off hydroxide as a leaving group. Effectively, this is a bad leaving group. What's left out of this mechanism is the A in LAH, which is the aluminum. The aluminum as a +3 metal is really stabilizing this intermediate, and it's going to be bonded to this as it leaves. So this hydroxide will be bonded to the aluminum, and that stabilizes it as a leaving group. But effectively, when this occurs, then we just have an aldehyde. And so your second equivalent of hydride can then attack again. We lose the regenerated carbonyl. And we end up with an alkoxide, which then gets to the product when we add in the water to neutralize the solution. And so that's how this reduction will occur with carboxylic acids. For acid chlorides, it's effectively the same mechanism, only have an even better leaving group in the chloride, but the mechanism's the same. And so, for example, with an acid chloride, we can reduce that down to an alcohol. Again, identical mechanism, but for example, this aromatic acid chloride, not a big deal, just reduces down primary alcohol. If you want to see the mechanism, we already have it written out right here for a different one. If this was just an acid chloride, that means this would be a chloride down here. That chloride just leaves, and then you would get to the alcohol that's reduced. So again, the mechanism is exactly the same. For esters, again, same mechanism. hydride will attack. Instead of having hydroxide leaving, we'll have methoxide as the leaving group. This will go through an aldehyde intermediate. And so we get, again, a primary alcohol. So you're always getting primary alcohols as products in these reactions. You can work through this mechanism in the same exact way. For amides, it's a little bit different. The mechanism's different. You're not responsible for this mechanism. It's in the book on page 769. It's a little bit more complicated than these other ones, and it's only specific for the amide. For amides, the product that you get is different. If you paid close attention to the mechanism in the other reactions, it was always the carbonyl oxygen that stayed on the molecule. In these examples here, it's the carbonyl oxygen that becomes the aldehyde oxygen that then is reduced to the alcohol. In this case, with amides, carbonyl oxygen is actually removed from the compound. So that's the oxygen that gets cleaved from the molecule. And so an amide is just reduced to an amine. And so, for example, if you had a tertiary amide, you'd get a tertiary amine. A primary amide would be a primary amine. Whatever is bonded to the nitrogen will stay there. If those are hydrogens or carbon groups, it doesn't matter. The reason for this, as you'll see in the book, basically in the mechanism, when you have a carbon-nitrogen bond or a carbon-oxygen bond, you're looking at O- or N- leaving the molecule. Since N- is much less stable and is a much worse leaving group, it doesn't leave. The oxygen group acts as the leaving group. And so you maintain the carbon-nitrogen bond in the product. So we can do these as examples. Here we have a secondary amide. Predicting these products is extremely straightforward. All you really have to do is redraw the starting material, except forget to draw in the carbonyl. There's going to be two hydrogens that take its place, and that's it. There's no rearrangements that occur. We don't need to worry about the mechanism, so these are really straightforward. A really good summary of all these reduction reactions is on page 770. And that's table 20.1. So it's really good for reviewing these. Right now, let's put up a couple practice problems, and that'll be it. Just strictly looking at predicting the products. So go ahead and work through these, then I'll put up the answers. For this bottom one, you can assume there's a large excess. Lithium aluminum hydride, it would not be very selective, it's too strong. Got an ester. For the ester, it's going to be this oxygen, the carbonyl oxygen, that stays on the structure. And so it's reduced to a primary alcohol. This ester group here gets cleaved off as a leaving group. And so we just get benzyl alcohol. To predict the products of esters, essentially you can pretend that the ester group was just an acid, because whatever that alkyl group, if you replace it with a hydrogen, you get the same product as you would with the carboxylic acid. For example, this same reaction. But that might be an easy way to remember it, because it kind of gives you, the power to predict two different reactions just by condensing them into one. Here with an amine, again, we just learned this trick. You're simply copying this structure, leaving out the carbonyl, and you can't go wrong, no problem. Down here, having two of these groups. You end up with an almost symmetrical product. Make sure you count your carbons here. Again, it would be both these carbonyl oxygens that were maintained in the product. But that would be our end result. We'll stop here in chapter 20. Next, we'll be moving away from oxidation reduction. So it's all these reactions are definitely important, and the mechanisms I presented are the ones you should know.